who cannot make it. Yeah. Other than that, how have you been? Hello, Yara. Hello, everyone. So, what is the plan for today? Guy has had a question that we tried to discuss over email, but he's still a bit confused. This is one, probably discuss it as a class, as a team together, and probably I can listen to what you think. Two, I want to finalize final exam date. We already have something we decided on. Probably we can confirm it. We are a small class. We can directly decide. Three, I want to finalize diffraction to be able to give you the results for you to do this lab. I was not in a hurry because I know you were still working with optics. So it doesn't make sense to overwhelm you. It will be good to sit and discuss diffraction a bit because last time I confused you by fixing the figure, changing the equation. I was not expecting this. So it will be nice to do it now. And eventually, I want us to do the photoelectric effect. Also, one of my very favorite theory, not the lab itself. I'm going to tell you a bit about the lab and why the lab could be a bit overwhelming for you. I mean, the procedure, not the experiment itself is very easy. You just have to click this, measure this, click this, measure this, nothing to worry about. But the procedure of how to calibrate your equipment and how to understand what's happening because you cannot see anything. It's basically electrons flowing and you cannot see. Most of it is not visible to you. So I would want to discuss everything again. All right, now talking about Guy's question. Probably I can throw it at the end of the slide because I need something to write on. So let me try to paraphrase what Guy asked, just for you, Guy, to see if I misunderstood or not. So Guy is discussing, and let me use a reasonable color. If you have a prism, he's discussing dispersion. So if you have a prism and you have white light, and white light is going into the prism, whatever, the glass, anything you want to call it, white light is going to go through the transparent material. At some point, you will see that the light rays, I will not put colors now because I don't want to confuse you. Anything, I'm going to use red because red is visible on blue. You will going to have some dispersion of color. And the question for Guy is, he wanted to try to understand why red behaves as such while purple behaves in a different way. And how is it related to the angle and how it is related to the N. By the way, N is the index of refraction of the glass. Outside we have N equals 1 and this is N equals 1, okay? So what I was trying to explain to Guy was twofolds. And Guy, please unmute and stop me if I'm saying something wrong. First of all, you need to discuss the relationship between wavelength, and for me, the wavelength is the color, and N. This is one thing. Another thing, you need to discuss the relationship between N, small n, and the angle. And under no condition, I want you to write proportional, inversely proportional. This is very important, and probably Guy was eventually confused because of this simple idea. Never discuss two identities increasing together to be proportional unless you have double, double, triple, triple, like the ratio is constant, okay? The wavelength and N are not proportional because for all the different colors, N was changing just a bit, Guy, by the second decimal probably. So this sudden change, this tiny change, while the wavelength was doubling, between purple and red, we have 400 nanometer micrometer versus 800 micrometer. It's like double, and N will not double, so you cannot say proportional, okay? I think I need to open optics. Do you think I have it in here? Because I would want, yes, this is what I want. Optics 2 or 1, most probably 1 or 2, 1 or 2, 1. Okay, so yeah. I just want the table where N is a variable of, yes. So you see, N is practically constant. And N for violet, where the wavelength is less, is bigger. So don't say inversely proportional. So I'm gonna say simply, back to this one, that probably they behave in a different way. Or you can simply say without any worry, and let me change the pen, that when the wavelength decreases, that's purple, and increases. Okay? Now Snell's law states the following. Snell's law states N1, okay, change the color to have, why not use black? Because we do have blacks. So N1 sine theta 1 is equal to N2 sine theta 2. That's for Snell's law, okay? And what I was trying to explain to Guy here, that dispersion is happening mostly on this level, while the light ray is traveling from the inside to the outside, from glass to air. So this is N sine theta 1, and I'm gonna assume theta 1 is mostly the same for most of them, most of the colors, is equal to 1, because we're talking about, you know, the air outside, 1 and sine theta 2. And here the question is, if I need to discuss the relationship, Guy, between N and theta 2, do you see them proportional or inversely proportional? N and theta 2 are not proportional and they're not inversely proportional. Just a second. Yara, do you need me? Yes, you can. Of course you can. Yes. All right. So let me say it again. We cannot say proportional. If you want to say proportional, say N and sine theta 2. You know? Anyway, your job is to know who is increasing with who. I'm going to simply say, as N increases, the angle is gonna be more. Am I right? Let me see. The angle is gonna be more. Now let me take a simple example with a thinner pen. Let's say I have this, I have N, and I have this. Okay, I know for a fact that, okay, excuse this. So it's gonna go out like this, you know, bigger angle, because I'm moving from a more refractive medium to a less refractive medium. So this is theta 1, this is theta 2. Now what happens when this one is bigger? This one is gonna increase, and it makes so much sense to me. Okay, so N is not the outside index, it's the inside index. And now the question is how it's related to the wavelength. I'm not reading you, Karine, yet, because I don't want to confuse myself and everyone else, but I'm going to read you in a second. So now let me go back to this one. Talking about purple, and probably if I insert a text box, it's going to be easier. So purple has a small wavelength, and it has a big N. So it's gonna end up with a small angle. No, big angle, big angle. So what does it say? Which means big angle with respect to the normal. This is very important. So yeah, where's the pen? Pen, I need pen. So big angle with respect to the normal. So does it mean that purple disappears first? So yeah, this is what it says. So I'm gonna say so, and then I'm gonna read you, Karine. Purple disappears first, and red disappears last. Okay? Okay. How do you feel about this, Guy? All right, let's go back. Okay, let's go back to what Karine was saying, because she said something. Sine theta and theta is the same, no? How are they the same? If theta increases, sine theta increases. All right, they increase together. So sine theta is an increasing function. But if theta is doubled, and I want you to try this in degrees and in radians, if you take theta to be whatever 10 degrees, and then you do theta equals 20 degrees, the sign will not double, so you cannot say proportional. Okay? And I know for a fact that probably you missed that in most of the labs, By now, it's your second semester, I suppose, or more than second semester, it's totally forbidden to say proportional, inversely proportional, unless you can prove a constant ratio. And I really want to stress on this one. It's very important. It's not only physics, it's any science, okay? Not any science, even if you're talking finance. Don't say proportional right away, okay? Yes, we need to have a constant. Thank you very much. Yes, they increase together. You definitely need to know increase or decrease, or otherwise it will be very difficult to handle. Okay? Like, how would you analyze and observe and discuss things? You need to say increase, decrease. بس أنا مشكلتي مع جي بلش الإيميل proportional and I was like no, and he was like what, and it was a big confusion, you know. But eventually Guy's analysis was not wrong. Guy's analysis had only one tiny mistake. He was assuming that light was traveling from outside to inside. If you do inside to outside, n is gonna be opposite, and that's why you are having something completely opposite to any results you would have. All right, if you want, you can take a screenshot of this, Guy. I'm sure it's gonna help you. Before we go back a bit to diffraction, and I would love to discuss this with you again, and I need to ask you some questions. Yes, Roy, ask me, please. By the way, thank you for joining today, even if it's late. I really appreciate that. And cheers for our last session. Yes, Roy. Roy has a question. All right, Roy, if you need to speak up, I want to, could you please elaborate briefly the behavior of colors? All right, so you mean behavior as in what happens eventually. So, for total internal reflection, I just saw your message. That's so true. I did not mean to ignore it, but I totally forgot. Okay, so yeah, we can discuss it mathematically because I believe it's also one of the many confusions you have. I'm gonna take the example that you had in the book. Let me try to remember. It looks like this, the one we had in the experiment. And the light ray was traveling like this. And here you had the total internal reflection. Let's say reflection happened here. Okay, so basically you had purple, then let's say blue. Okay, I couldn't see it هيدا. Old lady did not see it. Then green, ما إلا تعمل blue أصلا ما بينت. Then I don't know, eventually red. Okay, so all right, so and I'm gonna draw the normal like this. When you have refraction, it means you are just below the critical angle. Okay, obviously purple is gonna disappear first, because I remember that from the experiment itself, and because it's very well related to the dispersion we had previously. It's the same thing. So purple is gonna disappear first. Disappearing first meaning, so purple is going to disappear first. This will tell me that purple has a small or big theta critical. Has a small theta critical. Okay, why small? Because as I'm turning, increasing theta, increasing the incident angle, increasing, it's gonna disappear. So we reach theta critical for purple, and then we keep on increasing until we reach the theta critical for green, which means it's gonna be bigger. So the smaller is the one for purple. Now let's use Snell's law and see if the theory would actually be similar to the observations we're having. So Snell's law states n1 sine I1 is equal to n2 sine I2, or let's say theta 1 is equal to n2 sine theta 2. All right, so again, the light ray is traveling from inside to the outside if refraction happens. So this is n, and theta 1 is gonna be theta critical, sine theta critical, and outside you have 1 for air, and sine 90 is 1. So you'll end up with sine theta critical that, yes, behaves like theta critical, to be 1 over n. Okay, we already said previously that for purple the wavelength is small and n is big, so n is big, theta critical is small. Which makes sense and which is very similar to the observation we just had. So I'm gonna type it with a different color. Hopefully it's gonna allow me to change the color. So I'm gonna say purple has a small wavelength. So it has a big N. So it has a small theta critical. So this is exactly using Snell's law. Okay, so Snell's law actually gave me the same thing. Roy, is that exactly what you wanted?
Yes, Doctor, part of it. But what I meant was, let's suppose that we have this figure and tilted the object slightly in a way that all the rays are being internally reflected, but red isn't. It's being refracted. So we will observe the red ray. However, the ones that are internally reflected, will they overlap over each other, or
Yes.
will they be dispersed inside the? So they are overlapping.
Good question. So Roy is saying, okay, we know that red is still outside, but the thing inside, all right, so let's say theta critical is 45 degrees or anything, 45 degrees. If you reach 47, three colors are gonna be reflected, but the incident angle is 47. The reflected is 47 for all of them, for the all three rays. So they're gonna overlap, of course. There's no change because you're still inside, and the reflection has nothing to do with N. So let's say purple, blue, and green are reflected. Reflection, they have different N, right? So glass behaves differently for purple, blue, and green. So N is different for purple, blue, and green. However, reflection itself has nothing, it's not related to N. So they're gonna reflect with the same angle, which is equal to the initial incident angle. So yes, overlap. The angles are equal and independent of N for reflection. That's true, Yara, for reflection. So Guy is saying purple has the smallest theta critical and the largest angle of refraction. Yes. In this case, okay, I don't like generalities because generalities is what makes you confused, Guy. So yeah, in this case, talking about this prism, this specific shape, yes. Because what if something is happening in a different order? A total internal reflection will never happen in an opposite order from air to glass. It will always be from glass to air, which makes your job a little bit easier. Same with dispersion. So yeah, I would say, Guy, your statement is true. Cool? All right. Who stayed with me last time after the session? I can't remember. Probably Roy or George or Giscard. I can't remember who stayed with me. Probably.
It was me, Doctor.
Yes, Roy.
We talked about the vast difference, yes.
Yeah, okay, so it's not in this session, it is in this. Yeah, and then we talked a bit about diffraction, and I want to repeat what I told you to the whole class. And I'm happy we're recording now so we can discuss it, especially with the students that cannot join us today. So let me try to remember what I told you. I was doing this calculation, and at some point I messed up. So what is the thing? I want us to consider all this. احنا شو بدنا نسميها as A. So A is the width of one slit. So let me remind you, I'm doing the fraction. I have only one slit, and A, the size of one slit, is what matters. For me to consider this triangle that I'm gonna color in yellow, and I hope you can see, I need to take not A, but half of A. So this size is gonna be A over 2. I'm gonna go back to black. So A over 2, okay? And I'm gonna take this triangle to find the path difference. If I do the path difference, I know I was discussing a bit that there is some assumption because eventually diffraction happens when you have superposition between all the tiny little. So when you have this slit, it's one tiny opening, isn't it? According to the Huygens principle, the slit behaves as if you have on the margins of the slit like an infinity of numbers of sources of light. Like instead of having one source of light, you have an infinity of sources of light, and they all will give you waves, and the waves will superpose on the screen. So by saying that I need to add up wave coming from source one and wave coming from another source, this is a lot of simplification and estimation, because eventually we're gonna do much more than this. Okay, yes. So if I need to take the triangle in yellow and find the path difference, and the path difference, isn't it opposite to theta? Opposite to theta is basically sine, right? So I'm gonna say the path difference is equal to the hypotenuse sine theta, and hypotenuse is a over 2. So it's a equal to a over 2 sine theta. Okay, now I need to go back to the figure that is here, and yeah, this is theta. So you have two theta. This is theta. I'm here. I'm not sure if you can see my pointer. And this is also theta. Why are they equal and opposite? There's the same because you have this to be perpendicular to one line. So how can I point at something for you to see it? So this is perpendicular to this, undo, and this is perpendicular to this, undo. So that angle is equal to this angle. All right. Now, if I look at this angle, I'm gonna, let's say, target it to M2. Okay. M2, M equals 2 is the second dark fringe. And for you to have a dark fringe, you should, the path difference should be an odd lambda over 2, isn't it? Okay, so I'm gonna write this back to black and write odd, I don't know if you can see it here, lambda over 2. Okay, let me fix it a bit. So it is odd horrible lambda over 2. Okay, so the thing is, now I can, all right, let me say it again. So for m equals 1, it's 1 lambda over 2. This is, I cannot say 2 lambda over 2. It's going to be 3 lambda over 2, and so on. Okay? So now 2 and 2 would cancel out. I will end up with a sine theta to be odd lambda. So this equation is not wrong, and the position of the order of the dark fringes is not wrong. The only mistake that probably we should be careful about is that m should be odd. Because if you replace m with an even integer, you will end up with integer even lambda over 2 will give you something proportional to lambda, and it's not a dark fringe anymore. Okay? Now that you have tangent theta is equal to lambda, so using this yellow triangle in here, you can do tangent theta is equal to lambda over d. And to be honest, this works so well only for the central fringe. So why not do the central fringe only? Because for the central fringe, or m equals 1, and probably I'm gonna type it in here for you to keep it. So for m is equal to 1, I'm gonna say theta is very small. So now I can say sine theta can be equal to tangent theta. And now we don't have the problem of odd and even anymore. So who cares if m is odd or even? What about we do it only for, don't we want the size of the central fringe? And if we know the size of the central fringe, or the size of half the central fringe, can't we discuss the size of any other fringe? And isn't that the purpose of the lab? So sine theta will be equal to tangent theta. By the way, I just replaced m by 1. So I end up by saying, remove the m because m equals 1, you will end up saying a is equal to lambda d over y. Now what is y? Y is the distance, the half the size of a central fringe, and I need to type it as well in here, and this is what you need to leave with. So y is gonna be half the size of the central fringe. And why is it important? Because it's equal to any other fringe. Okay? Yeah, this. So now if you see the equation again in the lab report, probably we can go to the manual. I have it open in here. and I should not scroll a lot. Should I? No, it's here. So you can easily find the relationship between the width itself and the separation. Yani the separation is y. Okay, the separation between two dark fringes is equal to y. This is the separation between two dark fringes. Okay, this is the separation between two dark fringes, and this is another separation between two dark fringes, and this is another separation, and this is another separation, which means it is equivalent to half the size of the central fringe. So the math that we did in here had two estimations. The first estimation, you have an infinity of number of sources that superpose, and you need to come up with something reasonable. And the estimation actually works because the slit is very small and the angles are very small. The second estimation we did, sine theta is equal to tangent theta, and this works only for the central fringe. So it works only for n equals 1. So you cannot use this equation and assume m is equal to 10 or not even 3. So yeah, so this works only for m equals 1 because you just said sine theta equals to tangent theta. هلا m equals 2 مش كارثة لأنه anyway the angle is still small. But to go up to M3 and M5, I don't agree a lot with the lab report. It's not very accurate, okay? Anyway, I think you got the idea. And what's the most important thing that you have to leave with talking about diffraction and interference is the relationship between the separation of the size of the fringes and A and big D and B. Is it called B? Back to the table in here. So this table is, yeah, A is the size of this something, and D is the size of something else. If I'm not wrong, D is the distance between two slits, and A is the width of one slit. So you have the separation between fringes, you have the wavelength, you have big D, which is the distance to the screen, and you have the size of one slit. And how are all this is related? This is very important for you to understand. One more thing, you need to know how to describe a diffraction pattern or an interference pattern. If I give you a pattern, you should be able to tell if this is diffraction with one slit or diffraction with two slits that people would call interference, okay? Interference with one slit or interference with two slits. This is what I meant, but doesn't matter. Like, you need to know the difference. Can I say that we're okay with this lab and we can move on? Yes? Do you think you have some confusion on any level? And it's okay if you need time to grasp, we can meet again. We have now a lot of empty slots. We can meet again anytime you want. Guy, next time, instead of you sending email, we can meet right away. Okay? At any time you want. Yes, please talk to me for me to know if you guys are okay with this lab. وينن البنات? Where are the girls? They're quiet. Yara, Karine, Anna, everyone. All right. Anyway, I'm gonna start now with which one? Which one? This. Yes. All right, Yara. Of course. Of course, Yara. We can meet anytime. Just tell me. I will go on WebEx. All right, Anna. Yes, of course, Karine. I urge you to change it. Of course. You can submit your lab reports again and again anytime if it's not graded. And by the way, even if it's graded, yesterday I told Ali, not in your class, he wants extra work and extra grades. I asked him, why don't you fix your old lab reports and submit again? I can give him some bonus questions. So for me, bonus grades, I mean. For me, submitting again is a way for you to improve and to fine tune your lab, and why not? Even if it's graded, but I will not grade it again, probably give you some extra points if applicable, okay? Yes, Roy, don't worry about it. Now that we're done with all the live sessions, I will be focusing on finishing up the grading, okay? Yes, so don't fear it's only you. It's basically you and two other students, okay? All right, so now the photoelectric effect. that I suppose to be very interesting. This is a picture I found. I think it's simply art. I don't know how real this picture is. Just to start my talk, discussing light to be a particle or a wave. The outline I'm gonna follow is talk a bit about duality of light before discussing our actual lab. Okay, yes, it is both. Can you tell me, Yara, in which case light behaves as a wave and in which case light behaves as a particle?
I'm not sure, but I guess the particle property comes from the photons when it's interacting with other particles. Right now,
Yes.
the wave is just when it's propagating as energy.
Okay. How do you find the energy of a photon? Do you remember? And I love the word
It's
interacting.
H nu.
H nu. All right. So I found this chart that I never saw before, and it's basically famous because it's everywhere, but I really did not see it before. I'm gonna use red probably. So it says that, so this is particle and am I using reds? Yeah. Is that reds? Okay. So this is particle and this is wave. This is Newton, I suppose, and this is de Broglie, although I'm not sure, because they had eventually, or Planck, I don't know. They had, so this man is only talking in the video, and that's a screenshot. So this man is not known. Something Anderson, I was checking his name. So basically, they were debating, and I do remember Newton for that. They were debating for the light being a particle or not. And eventually, Einstein took part of the photoelectric effect theory. Yeah. So, and you have the Einstein equation coming up in a while. So, when you have interference and diffraction, and this is lab 9 for us, you have to consider light to be a wave because we were discussing superposition of waves, didn't we? And you were discussing the wavelength, if they are in phase, the path difference is in integer times lambda. If they are in opposite of wave, in opposition of phase, you had odd lambda over 2, so they cancel out, and you have dark fringes and bright fringes. All that is taken into account that the light is a wave. However, if you need to talk about photoelectric effect, this is exactly what Yara was talking. It's an interaction between a photon, not a wave, a particle of light of a certain energy that is not half mv squared because you don't have the mass of it. It doesn't have a mass. So to find the energy of a photon, I'm gonna start with writing it here. It's h times nu, and nu in your physics course means the frequency of the wavelength. H is the Planck's constant, and that's why I thought probably this is Planck, but I need to, yeah, and by the way, the wavelength can be found online in joules times second, in joules times second, or in EV times second. So you have two different, it's the same, but like be careful with the unit. The frequency had a unit of 1 over second, so you will end up with an energy for the photon in joules or in EV. EV is the electron volt. So yeah, I'm gonna take into account the photon to be a particle, like packets of energy interacting with other particles that are basically real particles with mass. I'm talking about electrons. So that's why the title is photoelectric effect. I don't know if you ever covered that in the course. Can you please tell me a bit? Because I'm very interested to know what you already know about this. And probably write it under this slide. Okay, you finished in the course. Awesome. So you should know everything about the photoelectric effect, which means don't need to go back to your, how can I call it? Your high school material. So what is photoelectric effect? Anything. So throw any idea at me, even if it's wrong. We can write it down. Photoelectric effect. What do you remember?
Is it when light interacts with a metal and it extracts a proton?
Okay, light interacts with a metal and it extracts what?
An electron, sorry.
Electron. Okay, anything else? Anything else you remember, like keywords? It doesn't have to be explaining what is photoelectric effect. What keywords do you remember? If the level of energy decreases, a photon is released. All right, I'm gonna say that here that Karine is talking about some level of energy, but she's not sure about quantification of energy. Quantification of energy. Probably we can discuss that as well. Discrete. Although what just happened, although this is not very visible, it's definitely part of the experiment, but not very visible in this experiment. Discrete energy levels. So when we say discrete, it comes from the fact that light is a packets of energy. That's the most discrete thing. Discrete versus continuous. Energy of ionization. Okay, you're going there. So energy of ionization. Any ionization. Anyone remembers anything about work function, about a well, about kinetic energy, about intensity of light, anything? All right, so I'm talking to a very small group. We're 7 participants, and that's a lot. Thank you so much for your input. Let me start by showing you the lab report, and this is the first time I do it. I'm not gonna start with the theory, but with the lab report. I have, you know what's an aperture? An aperture is an opening, okay? So an opening receiving light. I have a 4 millimeter diameter aperture. Okay, Roy is saying the remaining E is expressed in kinetic energy. Yes, exactly. And this is Einstein's equation for the photoelectric effect. Yes. All right. So I have 3 different types of conservation of energy. You want to call it? Yeah, why not? So we have 3 different types of apertures, and we can simply, it has a rotation, like you click, click, click to change the aperture, and you can see change in size, change in size. And I mean by aperture, it's like a, what do I call it? It receives light. It's not a filter, but it blocks the light. So it's simply an opening that would block or unblock the light depending on the diameter you want. So by changing the aperture of my opening before the experiment, I'm varying a very important parameter that I'm gonna call, what shall I call it? Intensity of light. Intensity of light. Intensity of light. So this is one parameter, intensity of light. Now I'm gonna send different colors. And by changing the colors, am I changing the intensity of light or something else? You tell me. Changing the color of light, changing the wavelength, changing the frequency, changing the energy eventually. Okay, yes. Thank you. I love this, Yara. So Yara is saying that since the energy of light is h nu, and nu is the frequency, h times frequency, by changing the color in here, we're changing the energy. So in the table, I'm changing the energy of light. Between A, B, and C, I'm changing the intensity of light, okay? These are some wavelengths. By the way, how would I change the color? I will be using a mercury lamp. And this is the spectrum of a mercury lamp, okay? But I cannot allow mercury to send me all the colors in one shot. So I will be using a filter. I will put the yellow filter to receive only yellow, the green filter to receive only green, the blue to receive only blue, the purple, and then the ultraviolet, okay? And then definitely, so this is the spectrum of the mercury lamp. And you can calculate the frequency by simply, how do you calculate frequency from wavelength? Again, how did you remember any of that? Yes, we're gonna assume, and that's an assumption, that frequency is c over lambda. Remember, c is the speed of light in vacuum, and I don't see our lab is in complete vacuum. So that's an assumption. I know in air, the speed of light is gonna be very close to the 1 to 3 times 10 to the 8, so I don't think there's gonna be a big difference anyway. But yes, that's an assumption. Now the stopping voltage potential, I'm gonna explain it later, but it is the kinetic energy of the electrons. So as you can see, yes, you can say it's a source of error, Yara, but it's not a very big source of error. Like it's not major, but yes, it is part of the sources of errors. Yeah, all right. So by changing the color of the light, do you think the kinetic energy of the electrons ejected is gonna change? And by changing the intensity of light, do you think the kinetic energy of the electrons are gonna change? So is the kinetic of the electron related to the color or to the intensity of light? And so on. All right. So this is the main discussion of this lab. Okay. So now, because E of light changes. Yes, so you're trying to answer, I think you know the answer. So Hussein is saying changing the intensity, change the amount of the electron and not the Ke. That's also true. We're gonna see if our experimental results make sense or not, and if they're related to the theory or not. By the way, if we measure the current in the circuit, you know the current is related to the number of electrons and to their speed. So it's really tricky experimentally to be able to know all this. What do we measure? We want to measure the kinetic energy of the electrons and their numbers, you know? So yeah, we're gonna see how it's gonna work. Now what we have the theory, this is an incident light. 2 photons will eject under some conditions 2 electrons that we usually call them photoelectrons. This is a metal surface. So this is Planck. Let me see if he looks like the other guy. I did not notice this picture before. This is Planck again. This is Planck again. Where's Planck? Planck. I don't know if this is the same guy. عنده مستاش. شوفوا له. ما عنده مستاش. ما بعرف. This figure is weird. It is not. Anyway, so if I need to remind you about the Einstein's theory or the Einstein's equation, when you have E energy coming from the photon equal to h nu, okay, all this energy would go to lift the electron from a certain well, and you need an energy equal to W for the electron to be able to escape, and all the remaining energy will go into kinetic energy. So kinetic energy of the electron is the given energy to the metal minus how much you should pay for the electron to leave its nest. Okay, yes, ionization by definition is when the electron is free out of the metal. So W is how much you need for it to get ionized. So if you want, Yara, to make it simple, we can say it's the energy needed to lift the electron from the ground state to the ionization level, right? That is usually of E equals 0. This is where the electron is free, and you can say the metal is ionized. Now the extra energy is what's the word, not quantized, it's continuous, so anything extra will go into kinetic. But for it to be free and to gain kinetic energy, you need W, and exactly W, not less. Okay, W is called the work function, and it is related to the metal. Each and every metal has its own W, and usually W is given in electron volts. That's why you need to calculate h nu in electron volt. And why not keep the kinetic energy in electron volt? By the way, 1 electron volt is equal to, do you know, in joules, 1.6 times 10 to the negative 19 joules. All right, it's simply replacing E by the elementary charge, and you will have coulombs per volt, which is joules. Okay, so yes, we're gonna work with EV a lot. Just convert by multiplying if you want it in joules, by multiplying by 1.6 times 10 to the negative 19, and probably you're gonna need that. All right, so what's next? This is a bit similar to the experiment we're gonna have. We're not gonna use a torch of light, obviously. We're gonna use a mercury lamp. It's basically a lamp very similar to the ones you have at home. It has a bluish light. In the lab, it has an adapter, and we click on, and we need to wait a bit for it to heat up. Sometimes we say 20 minutes, but I think in 15 minutes it works. So usually when the students come in, they click it on, then we do a briefing because they need to wait for it to warm up to give all the spectrum needed. And it's gonna be shown on a piece of metal, like a photocell, and the electrons are gonna be ejected. You're not gonna see it, obviously. You have an ammeter, and you have a power supply. Okay, you can see that this lamp or source of light, let's call it source of light, you can vary the intensity of it and you can vary the wavelength of it, because that's the experiment, changing the wavelength and changing the intensity of the light. The current, we use the ammeter not to measure the current, but to make sure the current is zero, because our job is to stop the current. So if I apply, do you see it in here? And I love this. This is exactly what we do in the lab. If I apply a voltage that is negative 0.95 volts and I get zero current, it means this is the opposing voltage to stop the electrons. And due to the conservation of mechanical energy, kinetic plus potential is equal to kinetic plus potential. When the electrons will stop, they have an electric potential. How can I call it? Potential energy electric is equal to the initial kinetic energy when I had no stopping potential. Okay? The kinetic energy is half mv squared. I'm talking about the mass of the electron and the speed of the electron. And the potential energy electric, do you remember how to find the potential energy electric? Or what is it that depends on? Yes, it's Q times V. Q in this case is 1e. We're talking about an electron and I'm taking absolute value. So it's gonna be, okay, I'm gonna write Q times V as a start. So Q times V is gonna be equal to kinetic energy. So I'm gonna say the stopping potential is negative 0.95 volts. So the kinetic energy of the electrons is 0.95 EV. And then I can convert to joules if I want. Or I can simply replace Q by the charge of the electron, which is 1.6 times 10 to the negative 19, times this voltage to find the kinetic energy of the electrons. There's no other way to measure the kinetic energy of the electrons. I cannot measure the mass. The mass is known. I cannot measure their speeds in a very precise way. So the best way is to create a potential difference opposite to the photo voltage or the photo current happening because of the photoelectric effect. Yes. So Yara, due to the photoelectric effect, you have a current that is not zero. So what I do, I get a power supply and put it in such a way, like connected in such a way, to have a current opposite to the one given by the photoelectrons. My job is to stop the electrons. Yani, I need to create an electric field between the plates in the same direction of the electrons, yani an electric force opposite to the electrons to stop them. If I can tell how much volts I need to stop them, I can deduce the kinetic energy of the electrons. Let me give you an example. If the kinetic energy of the electrons is 2 electron volt, I need negative 2 volts to stop them. If the kinetic energy of the electrons is 3 electron volt, I need negative 3 volts to stop them. You see? How do I know they stopped? I look here. So the job of the students in this experiment is to increase the stopping voltage in the negative way until they get zero current. And trust me, it's 0 times 10 to the negative 17. It's so precise. You will have a very big amplifier just for you to be able to see the current down to 17 decimals, something like that. All right, I'm not gonna show you a video of the experiment now, not until you understand fully the experiment itself, because the video of the experiment will show you a lot of big devices and I'm too scared you will be overwhelmed with this. And you have a power supply, you have an ammeter, you have how can I call it? You have an amplifier, and I mean by amplifier something that will show you the current down to 10 to the negative 17. And you are required to zero the current, like to calibrate. How do we calibrate? I switch off the lamp, and by switching off the lamp, I should get zero current. So I need to zero the whatever, the measuring tool, the ammeter. And then I need to start putting the light on with the intibah. If the light is not warm enough, it's not gonna give me the wavelength I want. And then I should start increasing my stopping potential in the negative sense. يعني بيكون زيرو بصير negative 0.1 negative 0.2 and I keep on increasing it in the negative direction until I get zero current. When I get zero current شو بقول? This is the stopping potential. In other words, حتى volts بتصير EV بتصير kinetic energy. Just change the unit from V to EV to know the kinetic energy. Okay? هلا انتو, for you it's not gonna be tough. You simply need to know that whatever value you have here, just change the unit to EV and it's gonna be your kinetic energy for the photoelectron. Okay? I will revisit this again if needed. Now, back to the theory. You can see red. Red has a small frequency, so small energy. No electrons are ejected. So the energy is not enough to overcome W. By the way, in some books, W is called phi0 probably. When I use green, green has a bigger frequency. So it has an energy a bit greater, and apparently it was enough to release 3 electrons. I love the fact that I have 3 waves and nothing, then 3 waves and 3 electrons only. And this is nice because it shows you 3 waves only and you end up with 3 electrons only. However, the difference between these two is that the electrons here is, yes, that's true, Yara. The electrons here are faster. Does it show they're faster? So in other words here, if I need to summarize it, bigger frequency, which is opposite to wavelength. And yes, you can say inversely proportional for wavelength and frequency. So bigger frequency is gonna be bigger kinetic energy, but same number of electrons. And that was Hussein's intervention a few minutes ago, right? Same number of electrons, okay? And then this is another. Yes, because C is constant, I can say frequency and wavelength are inversely proportional. This is another diagram. I love diagrams because I hope they stay in your mind. So this is the wavelength and this is the energy. How about we focus on energy? Red light has energy, green light has more energy, and purple has more energy. This looks like dark blue, by the way. So red will give you no electrons. This is an example of potassium. Potassium has a work function of 2 electron volt. As you can see, you have 1.77, which is not enough. 2 is more, so no electrons. 2.25 is a bit more than 2, so you will have an electron ejected with a kinetic energy equals to the difference between those two. And this will give you the speed. I did not do the calculation, but I think it works. By simply doing the difference in energy, you find kinetic energy, then you convert to joules, then you do half mv squared. And anybody remembers the mass of the electron? Probably you're gonna need it. Mass of electron. I know, it's 9.1 times 10 to the negative 31 kilograms. Am I wrong? So am I wrong? Anyway, check it. Let me put a question mark so you to Google it, but I think I'm 90% right. All right, so you do have mv squared, you find the speed, and you see the speed is pretty fast. And then back to the purple or the dark blue or whatever you want to call it, you see 3.1 electron volt, which is fair enough, like more than the 2.0 needed. So you will have an electron that is even faster. Okay, yes. Thank you, Roy, for checking on me. All right, back to this one. So the question here is what happens if I increase the intensity? So can you remind me again? Let's say I have red, but instead of having 3 rays only, how about I add more intensity? Do you think any electron will be ejected? No electron will be ejected. But what happens here if I add more intensity? Can I have faster electrons? We cannot have faster electrons. We will have the same speed. Is there any difference in the outcome? Yes, we're gonna have more electrons. If I'm gonna assume one, that's 6, so I should use yellow, or it's okay to use red. Can I use orange? This. Okay, to draw more electrons. Make it a total of 6. And same here, let's say I have this and this. Probably I should use a blue wave because this is chaotic now with all these colors. More electrons, same speed. Okay, yes, Roy, more electrons, but the same speed. More electrons would be a bigger current, definitely. But the stopping potential is gonna be the same. All right, so the experiment, I already explained the experiment in the previous slide. So basically, you're gonna change the intensity, you're gonna change the wavelength, and you're gonna find the stopping potential. I was too scared that you will not understand what stopping potential is. Apparently you did. The stopping potential, just change the unit from volt to EV to find KE. Go back to Einstein's equation that I can write here again. The energy given by the photon, let me write photon, which is equal to h nu, or h frequency, is equal to the work function that I'm gonna keep W plus the kinetic energy. Where do I find the kinetic energy? I find it from the stopping potential by changing the unit from V to EV. And then I can convert to joules if I want to. But why not keep this EV? Because we need this in EV and find Planck's constant. Let's find Planck's constant in EV per second. So we need Planck's constant, and we can write it here so you don't have to find it on your own. Yeah, Planck's constant, let me see what unit they will give us. This is SI units, so we don't want this one. We want an EV dot second. Okay, dot second means per hertz, if you want to call it like that. I'm gonna take it. If you want, we can have both. I will simply take a screenshot for you to keep and throw it here because it's good to keep, and probably save the file under your class. Yes. All right, save as. That's our scratch paper, in other words, right? Okay. All right, so keep that in mind. Yeah, why not use it? I know that you need SI units sometime at some point, but if we can do the whole report in EV, why not? But eventually, probably they want you to, I don't know. All right, we'll see about that. I'm gonna go over the lab report with you now. These are the values because I don't want you to wait for the results. So I've been working on the results yesterday. And as you can see, as the color changes, you see an increase in frequency, because ultraviolet, by the way, ultraviolet, that's the borders, like it's between violet and the real ultraviolet that is not visible. Because when I put the mercury lamp on ultraviolet, what do I call it, filter, I can see some purple, you know. So this is like on the verge of being ultraviolet, so part of it is visible. Yeah, so you can see an increase in frequency. Increase in frequency would mean more kinetic, and you see more kinetic is happening. More kinetic, more kinetic. Now, if you want to see the difference between the size of the aperture, we can discuss this later. I want to give you some room to think for yourself. The question, they want you to plot the 3 curves of the stopping potential as a function of frequency. I want to discuss the unit, not the unit, the slope a bit. Where's my pen? Okay, if I plot stopping potential like V as a function of frequency. Let me see the equation a bit. Einstein's equation, what does it say? It says HF is equal to W plus QV, because I want stopping potential, so I replaced kinetic by QV. Now I want to plot V versus F, so I'm gonna write V equals, I need help, V equals to what? Help. Thank you, that was fast, Yara. Okay, I'm gonna divide both, so it's HF over Q, right? Minus W over Q. So you have, yeah, tiny mistake. So let me see, HF minus W, all of it over Q. All right, so that's my y-axis and that's my x-axis. Okay, I know everything is constant. H is constant, Q is constant, W is constant, Q is constant. So what does it say? So you're gonna have 3 lines on top of each other? Think about it, I don't know. So plot the 3 curves of the stopping potential as a function of frequency. Use linear regression to find the slope and the y-intercept. What do they represent? Okay, the answer is here in this equation. Deduce Planck's constant and the work function. So far, I don't see uncertainty. Compare H theoretical. In your case, be careful if you have joules or EV, and if you have EV, use H in EV per second times second as a theoretical value. Comment on your results. You can compare percentage difference, accuracy, precision. You cannot do precision here because you don't have the uncertainty. Sources of errors. Does the maximum energy of the photoelectron depend on the color? Explain your answer. And you have a lot of conceptual. This is a lot of conceptual questions. Does the maximum depend on the amount of light? Why or why not? And this is like possible answers to pick from. So all this is conceptual, just to make sure, I think like multiple choice for you to think about. And I don't want to read it with you. I want you to think a bit for yourself. And that's it. And this was scratch paper for optics. Yeah. Okay. So as you can see, the experiment is straightforward. Not straightforward, but I mean it's very well structured. You have a change in wavelength, then change in intensity. And one is constant. You have the intensity constant that change the wavelength, then another intensity constant change the wavelength again, intensity constant change the wavelength again. So one parameter at a time. So it's very easy for you to discuss what happens, and the plot is gonna be crucial because it's gonna show you everything you want. By the way, the plot is famous. I mean by famous, it's gonna come in any problem later in the course. So every time they ask you to plot this versus that, you should know what the slope represent and what the y-intercept represent and so on. By the way, H is known. However, W is not known. That's why they don't tell you compare the W you found to the theoretical W, because you don't know what the cathode material is made of. I'm trying to see if I can remember from the catalog, because I have the catalog. Cesium? Could it be cesium? I can't remember for real. I don't have a picture. I wish I did a picture with my phone. But anyway, if you find the work function in EV, what about you have a look online? What is it made of if you want, because they never ask you. To help you, you can Google physics lab. Was it Pasco? If you can see in the video, if the material are from Pasco, you can, this would help you. You can Google photoelectric effect equipment from Pasco. What is the cathode material made of? And discuss your work if you want, all right? Or you can simply look at the value you get and see if there's something online, like any metal or any cathode that would be close to it. I think it would be interesting. Yeah. And remember, your result will be basically related to those results, and those results were done by students, and I don't know how much I can trust those results. I still have the names of the students. And that's it for us. Yeah, so I'm ready to answer any of question you have. This is saved. Oh, yeah. One more thing before you go, and that's very important. This, not this one, this. I can see from our last discussion that you want your final exam to be Friday the 7th at 5 p.m. Please confirm. Let me write it here because you are the ones to decide. We have no other section and you have the first and final word for it. Okay? Yes. Final exam. Black. Are you still there? So, Friday, May 7. By May 7, we have 2 weeks. I'm going to give you 1 week to finalize your lab reports or a bit more. And another week. Okay. Wow. Okay. So Monday 10. Bala, we can do Monday 10. Okay. Monday, May 10 at 5 p.m. How good is that? Okay. By the way, you have a final, Karim. Okay. Can we pick another timing? If the final is, listen, sometimes having 2 finals that are reasonable in one day, if they're separate by, like, morning, and we can do it morning if you want. Karim, what time is your final? Hicks, you can have at least half a day because for physics lab, I will give you feedback and I need to know, I need to tell you, feedback means like a summary. So I don't think you really need to study a lot, but yes, you have to go a bit over the material. If you can tell us, Karim, when, I think it's gonna be late afternoon. People, do you think we can do our final exam, let's say Monday, 10 a.m.? You're not too many. So probably you don't have class. Heck, if Karine has an exam in the evening, she will have all the day to study. So 10 a.m. And to be honest, I don't have classes. Okay. All right. So Karine, most probably, so Karine has an exam. Let me write it down. Karine may have an exam in the afternoon. Okay. So Karine, most probably your exam will be in the afternoon. If it's not, if it's in the morning, we can take the afternoon for us. Okay. Okay. So I'm going to keep it here on our slide and try to stick to it. If you believe that I would forget to give you confirmation or I'm too late for you, just talk to me on the chat. Our chat is very quiet. It's okay if you want to bombard me with questions, if you want to remind me stuff, if you want to have some reminders or confirmations, talk to me. It's okay. All right? Yeah, so that's it for today. I'm gonna stop recording, but I'm staying here